All right, we ran out of time today, and I wanted to go over one additional problem just to give you another example of how we can use the things we know about the shear moment, the shear diagrams and the bending moment diagrams. So don't forget, we learned that the shear force has a discontinuity if there's a point force. The discontinuity has the same sense as the force does, so if the force is positive, it jumps up. The couple is a little bit more confusing. It does cause a discontinuity in the bending moment diagram, but if the couple is positive, that is, notice this one is counterclockwise, the discontinuity is negative. It jumps down. All right, so let's skip ahead. We found in these slides was we found a relationship. We found that the slope of the shear force diagram is equal to the distributed load. Remember the sign convention? And that is that if W is up, it's positive. If W is down, it's negative. So in any case, what we learned is if there is a distributed load, the value of that, the height of it, is going to be equal to the slope of the shear force diagram. If there is no distributed load, then the slope of the shear force diagram is 0. We also learned that the slope of the bending moment diagram is equal to the shear force. So let's look at this example right here. And the first thing that we're going to do is we're going to find these reaction forces at the wall by looking at the entire beam. In the x direction, we only have ax, so that's 0. In the y direction, we have ay minus the force due to the distributed load, which would be 4 times 6, which ay is going to be 24, and that's going to be kilonewtons. Then I'm going to do the moment about point A. I have MA, which I drew as counterclockwise, so it's positive. Then we're going to have the moment due to the distributed load. It's going to be clockwise, so it's negative. It's 24 kilonewtons in all, and it's going to be halfway along the beam because it's just a rectangle, and so that's going to be 3. So the support moment at the left-hand side is going to be 72 kilonewton meters. So we don't have any point forces, but we do have this moment. And remember, this means there's going to be a discontinuity. And it's going to be down a magnitude of 72 because the sense of the discontinuity for moments is opposite the sense of the actual moment. All right, so if I want to do my shear force diagram, now this time I can just sort of sketch it. So this goes to 6. I found that there was a force of 24 kilonewtons. That was the support force. And W is equal to 4. So dV dx is equal to minus 4 because it's down. So basically I found that this has a slope of minus 4, which is going to make this a straight line. It's going to come to 0 at x equals 6. So that is my shear force diagram. See how easy it was to draw? I could also write this. It's going to be 24 minus 4x is the equation for that. For the bending moment, I know that dm dx is equal to v, which is going to be equal to 24 minus 4x. So dm is going to be the integral of 24 minus 4x dx. And so that's going to be 24x minus 2x squared. And we also know that we start off at minus 72 for the bending moment, because remember, m sub a was 72, it was counterclockwise, so it was positive. So our discontinuity has the opposite sense, so it goes down to minus 72. And then it kind of comes up, it's a parabolic, but it's concave down. And when x equals 6, m is equal to 0, we can sort of plug that out. So the whole expression for m looks like minus 72 plus 24x minus 2x squared. And notice though, we just kind of drew and sketched these diagrams using what we learned about these diagrams today and the relationship to each other and the relationship to the distributed load.